This is question number 32 from 9.7. A pretty challenging problem. It starts being pretty reasonable at the beginning and probably gives people answers that maybe you don't expect. So I thought I should take a look at this. All right, so they give you two different numbers. They give you 3 cosine of pi over 3 plus I sine of pi over 3, and you want to convert that over to a complex number in rectangular form. So you've got an absolute value here of 3. That's going to be a 60-degree angle, and so it's all 30, 60, 90 triangle. This side's going to be 3 over 2. And then you multiply that by radical 3, and you're going to get 3 radical 3 over 2. Of course, this is your imaginary side. So as a complex number, you've got a real part of 1.5 or 3 halves, and you've got an imaginary part of 3 radical 3 over 2i. Second one has an absolute value of 2, or a modulus of 2. It's a 150-degree angle, so your reference angle is 30. So a little 30, 60, 90 triangle. This is 2, 1, radical 3. You're going back radical 3. That's your real part. So it's negative radical 3. You're going up 1 in the imaginary direction. So negative radical 3 plus I. Okay? So I went back and looked at the original equation, and it said it wanted your lead coefficient to be x squared, or actually I think they said z squared, but I used an x in my example, so we'll live with it. Remember, if you want this to be a root, you know, like if 5 is a root, x minus 5 is going to be part of the factorization. If negative 2 is a root, x plus 2 would be part of the factorization. So you're going to have x minus this, and I literally just wrote it like that. And then you're going to have x minus this other solution here, and I just wrote it like that. Now, originally, those are my two parts of my factorization. They're going to multiply to equal 0. Now, originally I was thinking, oh, I'll kind of work backwards off a quadratic formula and try to get these solutions. And then I thought about it and I remembered something. The quadratic formula is always going to give you complex roots that are conjugates, okay? And this brings up a really important idea that I don't think I ever, straightforwardly said, and that is the fundamental theorem of algebra that says that a quadratic is going to have those two solutions in the complex plane. That idea that they're going to be complex conjugates only happens if you have real number coefficients for your quadratic. If you have imaginary number coefficients, your roots don't have to be conjugates. And if you notice here, these two roots are not conjugates of each other, okay? So that tells me I'm probably going to have imaginary numbers in my final quadratic, and I'm guessing for those of you who are asking about it, that's probably where you're wondering what the heck's going to go on. So anyway, long story short, you got to multiply these two things. I wrote them down here. I started multiplying, and so, I took x times x, and I got x squared, and I took x times radical 3x, and I took x times negative I, and I got negative ix, and then I took negative 3 halves, and I multiplied it by x, and I took negative 3 halves, and I multiplied it by radical 3, and negative 3 halves, and multiplied it by negative I. And then I took negative 3 radical 3 over 2i, and I multiplied it by x. And negative 3 radical 3 over 2i, and multiplied it by radical 3, which, by the way, gave me negative 9 halves I when you multiply that out. Okay, and then I took this and I multiplied it by negative I, and I ended up with a negative 3 radical 3 over 2. Okay, so I've got that whole line right here, this next to the last line, okay? That's the unsimplified form, and by the way, that should equal 0. I didn't write that down, but it should. And I really just had to group it. I've got x squared terms, I've got x terms, and I've got constant terms. So I just have a single x squared term. I took all of my x terms and I factored out an x, and some of them had i's, some of them didn't. So I also, inside parentheses, factor the I out of these two terms. You could write that as negative I plus 3i radical 3 over 2 if you wanted to, inside parentheses. But this is the coefficient, so to speak, of the x term. And notice, not only not a whole number value, it's not a real value, okay? And then we had a couple of terms there that did not have x variables, that were just constants. And specifically, those were the negative 3 radical 3 over 2, the 3 halves I, and the negative 9 halves I. So 3 halves I minus 9 halves I is negative 6 halves I. That's negative 3i. And then, of course, I had this other part remaining from the earlier part. And so that ends up being my final equation. That's not a neat equation in any sense if you're expecting it to be that.